Hello everyone, welcome to my presentation. My name is Simona Mihaiță. I'm currently a senior lecturer in the University of Technology, Sydney, Australia. And this presentation is about our work on graph modeling approaches for motorway traffic flow prediction. I'm going to start about introducing you to the problem and then to the methodology in the spatial graph structure and also the two algorithms that we have proposed, the backtracking and the interpolation prediction algorithms. These have been applied on the Sydney M7 motorway from Australia, and I'm going to talk to you about the experiments that we have done and the results that we have obtained. So why is it hard to have a good, accurate traffic flow prediction? First of all, because there are large amounts of data sets that are being generated with a very high frequency in general for monitoring all sorts of traffic networks. Also, the structure of the network can be very convoluted and very complicated, and this can introduce high complexity. Also, we have the stochastic events, random traffic disruption that can occur all the time, which makes things very unpredictable. And also the spatial and temporal distribution of the traffic flow. This can cause direct or indirect congestion propagation. Oh, last but not least, there are a lot of missing outliers and erroneous data sets that can happen to equipment failure. So all of these problems makes the prediction problem very hard. We wanted to embed the graph structure into the prediction method. That's why we came with two algorithms that we have proposed and that I'm going to explain next. So the steps that we have taken is first to map the station to the geography and the layout of the motorway. And then we have built the graph structure of the traffic flow. This is just a snapshot which goes from station 43A down to station 33A. And we have three types of spatial configuration in our motorway. First of all, we have the straightforward stations. So as you can see here in this example, going from 19A directly to 18A. So we have this case is the passive traffic case, where we assume that the flow that is reported in the same time interval, the next time interval at 18A should be the same as 19A. However, we also have the exiting traffic case where, for example, the traffic flow reported at 4A will be next split into the traffic flow going straight at 3A and the traffic flow exiting at 3X. And we also have the third case where we call this the merging traffic case, where the flow from 12A and 12E merge into 11A. So given this structure, our algorithm adapts to this, and then we finally get the flow prediction. There are a few notations that we have made. First, for the flow reported at a random station S, let's say at time E, and keeping in mind the profile of each station and the interconnections between them are given by the graph structure with the mention that the nodes of the graph are our stations and the edges of the graph are actually the distance between the traffic stations. So what is our backtracking prediction algorithm about? So we want, for example, given a time t and the station v, we want to be able to predict p time points into the future, and we call this the prediction horizon by using the information from r points into the past, which we call this as a training horizon. So what is the aim? Is basically to just look upstream into the graph for a station, let's call it U, of the same type, right, which lies at R plus P time intervals upstream. I have to mention that the time interval between reported data points is 3 minutes. So we started by building the distance matrix between these two stations, right, during R plus P time intervals. And we basically transverse the graph up and down, and we detect all the entries and exits between them. And basically, we are estimating this flow based on what we have found, plus or minus the entries or exit traffic flow. However, when we have multiple time points, this becomes a little bit more complicated. So assuming that we are at time t and we want to predict at p equals to 2 into the future, which is basically 6 minutes into the future, and using the last 6 minutes reported data set, so r equals to 2, We will then have to have a look at the movement of vehicles across the station. So let's take the same snapshot from 43A to 33A, whereby we're looking at the positioning of vehicles passing through each station. By red rectangles, we mostly colored the flow reported by a straightforward station, whereas the blue with the plus, it's entry, the blue with the minus, it's exit. So keeping this in mind, we have to mention the fact that we are using all the real-time flow reported lastly. So this is actual reported data set. However, when you want to predict into the future, if we want to use all the interconnection through the graph, we have, for example, we need to use for p equal to 1 historical data sets that have been recorded. So we also wanted to try another method and wanted to have a look at how can we predict the traffic flow moving from two time intervals to another by taking into a more smooth transition of vehicles between these time intervals. So in function of the reported flow for each time intervals, we have built this, let's say, proportionate traffic flow estimation for each, let's say, time interval that the flow would move across before finishing the 3 minute time period. So this will be the estimated traffic flow that we have here, which is composed of the two proportional flows from these two intervals. If we would have to represent this, this would take this shape basically where we have like a much more smoother transition from one station to another. And we want to see if this makes any sense, if this brings a much more improvement or not to the current backtracking method. We apply this on the M7 motorway, and we have started to build the daily profile predictors, as you can see here, for each day of the week and for each time interval that has been reported. We have also signalized, unfortunately, in the data analysis, missing records and all zero or outliers, abnormal data points that have been reported, and we have proposed a method for this anomaly detection, which is currently under revision. So how did we do the experiments? So first, for the prediction setups, we used the 36 million data points, and the training period has been based on the outlier that we have seen. So the training goes from February to April, from June to August. Validation is done for month of September and testing for month of October. And we, in order to vary the past and the future time horizons, so we have done various combinations, either one step into the future using one step from the past, or two steps into the future, and so on. We have reached R equals to 5 or P equals to 5, which is 50 minutes into the future using 50 minutes from the past. And this is mostly due to the limitation of the length of the motorway. So we have used the station from 26A to 03A for this experiment. For the other one, we have used all the stations. So we have compared with, in terms of performance evaluation, with the daily profile predictors that you have seen earlier, and also with the VPNN, CNN, LSTM, and the hybrid CNN and LSTM. These are 4 deep learning models that we have presented last year at IEEE ITS Conference from New Zealand, and we wanted to see whether our graph algorithm this year are performing better or not. We have used as performance evaluation metrics the RMSE, R-square, and SMAPI values. These are well known in the literature. In terms of results, for the outliers first and the anomaly detection, when we have applied that, we have realized, this is, for example, the R-square for the daily profile predictor. As you can see here, after the cleaning, we managed to remove all the over prediction of very like zero or very small traffic flow records. The R-square for the backtracking scored around 0.95, and for the interpolation around 0.94, with 2 main regions of traffic flow that are nicely following the main trend line. And also in terms of RMSE, as you can see here, we obtained a low RMSE around 80, 90 for the backtracking and around 100 for the interpolation. These are almost 3 times lower than the RMSE obtained for the daily profile predictors, for example. Same story is being told for the SMAPI here, around 3.54 and 4.5 for the interpolation. I want to mention here that between 45A and 35A, the errors are higher. This is the interconnection between M7 with M4, another important motorway in Sydney, which tells us a story that when more complex network structure comes in, the errors might increase. When we did the method comparison with the other deep learning model that you see here, we realized that our two proposed algorithms, the backtracking and the interpolation, seem to outperform by almost 60% even the best deep learning model, which was LSTM. So RMSE and SMAPI tell the same story. This is for very short time prediction into the future of p equal to 1. We also variated the p until 5, right? So this is 50 minutes into the future, and we have represented the SMAPI and RMSE for when we are using the best past horizon. If you have a look here, we managed, so that our two proposed algorithms, the backtracking and the interpolation, they really overperform all the deep learning models until p equals to 3, after which indeed they have a decrease in their performance. So this tells us a story that if we want to do prediction up until 9-10 minutes into the future, the simplified graph approaches that we have applied are working 50%, almost 60% better than the deep learning. RMSE tells the same story, right? However, for long-term predictions, indeed, the deep learning seems to be a bit more stable and they provide better results. However, this was a surprising result for us in the sense that you do not need complex deep learning model in order to have a very good short-term traffic flow prediction for next 10 minutes into the future. And the two models that we have proposed are a proof of that case. So this is surprisingly and pleasantly to know that there are different ways of doing predictions other than complex structures. However, there are a few limitations. Our algorithms do not assume any branching structure, so we only have the main flow, we have the entries and the exits. However, as you have seen, when there is the interconnection between our motorway and another motorway, the error increases. We highly believe that this is more related to the data sets that are being transmitted, station equipment errors, but of course, we would love to be able to apply these algorithms into more complex network structures and even urban arterial networks to see how they perform. We also want to be able to test the performance of our current graph models against graph CNNs, which are very popular version of CNNs, and see whether that makes any sense. However, the pseudocode for the two algorithms is provided into the paper, so feel free to have a look and check it out. If you have any questions, please let me know by writing to my email address listed in this last slide. And also, if you're looking for PhD opportunities, get in touch and talk to me. Thank you very much for your attention.